Hello, welcome both to those of you who are here with us this morning and those of you who are watching online. I gather that there were a lot of viewers last year, and we hope there are this year. I'm Don, G3XTT, and it's my pleasure to introduce Steve Nichols, G0KYA. Steve was licensed in 1981. He's chair of the Propagation Studies Committee, and as he's also a very active member, I know, of the Norfolk Amateur Radio Club, which is doing better than my own Bristol contest group.
Oh, did we beat you again?
In the club championship events. No, it's a real pleasure. Steve is a real expert on propagation. He's written various books. He's written numerous articles, both for Ragcom and, dare I say it, Practical Wireless, of which I happen to be the editor at the moment. But Steve, over to you.
Thank you very much, Don. Well, the title today is HF Propagation, What Do the Numbers Mean? This is a title that was suggested by RSGB, so don't blame me if it doesn't go well. But basically, we're going to look at solar cycle 25 progression, and then all these terms, solar flux index, sunspot numbers, K, KP, AAP, what do they all mean? Solar wind, what is it? What is the speed? And BZ, we keep hearing about BZ, what on earth's that? And then we'll look at critical frequency and maximum usable frequency as well. So basically, just trying to take some of the mystique away from some of these terms, and probably we'll explain as we go through how useful they can be. And we'll look at solar flares as well. So where are we in solar cycle 25? Well, we are just where you can see it, just there. We're actually doing better than the prediction at the moment. Now, this was the official prediction from the group, which is, they take about 10 people's opinions and come up with a prediction. It's not the prediction that another scientist in America came up with. A guy called McIntosh came up with a prediction that said that this cycle was going to be much, much better than the prediction that the rest of the team came up with. And at the moment, it's looking like he could be right. So we're actually doing much, much better than we thought we might do. But if you look back at the previous cycle, 24, you'll see that it's very much up and down. So we can't read too much into that. And that's not unusual. The reason that if you look at solar cycle 24, you've got two peaks. Usually the sunspots peak in one half of the sun, one hemisphere, and then peak in this lower or upper or lower hemisphere at a different time, which is why you get this twin peak effect. And that may happen with us. But at the moment, we're looking for a sunspot maximum somewhere around 2025, 2026. So this is a great time right now to be on the air. Things are looking up, and they're going to get better over the next couple of years. So usually I've been giving this sort of talk around about 2020 when it's been rummaging around the bottom. So this is actually a good time to do it, and I'm quite excited by it. So where do we get these figures from? Solar flux index, K indices and K events. Well, the usual one I use are these two FTP sites. This, you can make a note of these URLs if you want, or I will make this available after the event as well. But this is from the daily solar data, and you can see the data from NOAA, SWPC, as a Space Weather Prediction Center. Gives us the flux, sunspot number, sunspot areas, and then the X-ray data as well. But what do they mean? Well, let's have a look. This was a shot of the sun from yesterday, October the 7th. No, it's today, isn't it? I think, which I put on last night. And you can see that we've got a solar flux index of 156 and a sunspot number of 139. Now, this is where people sometimes get confused. First of all, why do we have two figures? An SFI and a sunspot number? I think that's historical more than anything. And what are they? Well, the solar flux index is the strength of the radio signals coming off the sun at a wavelength of 10.7 centimeters. That's 2,800 megahertz. We can't measure the ultraviolet output from the sun on the Earth's surface because it gets absorbed. So we use the 10.7 figure as a proxy for that. It's not that the radio waves at 10.7 centimeters are actually ionizing the ionosphere. It's a proxy for what we think the UV output from the sun is. So we can measure that at ground level. It's never lower than about 65, 66, and can go as high as 300. So at the moment it's 150, so kind of midway between the two. And I think over the years I found that for 10 meters to open up to F2 layer propagation, we need a figure maybe in excess of 100. Once we get above 100, then 10 meters maybe can open up. If you've got the right month, obviously it depends. October's a good month for 10 meters, and November will be a good month for 10 meters, then it'll probably die out a little bit more. But high values generally indicate, as we say there, that it's sufficient ionization to support long-distance communication at higher than normal frequencies. So that's the solar flux index. So why have we got sunspot numbers as well? I think this is historic, really, that we've known sunspot numbers or been making note of sunspot numbers since about 1800s, I think. And it's traditional that we just carry on with it. But sunspot number doesn't mean, this is where people get confused, it doesn't mean, this, if the sunspot number today is 150, it does not mean there are 150 sunspots on the sun. Because we score 10 points for every sunspot group, and 1 for each sunspot. So the lowest it can really ever go is either from 0 is 11, because that's 1 sunspot in 1 group, scores 11. And if we've got 3 sunspots that are well separated, that's 3 sunspots in 3 groups. So that's 10 plus 10 plus 10 plus 1 plus 1 plus 1, 33. So you can see that for three sunspots, you've got a sunspot number of 33. So it does sound like you've got more sunspots than there actually are. And the lowest value you can get is obviously 0, and the highest number you can get is about as high as 286, which was solar cycle 19, which is a particularly good one. So that's sunspot numbers. And as I said, it's traditional because it goes back to the 18th century, I think, when we were making notes of sunspots. Now, how do the two correlate? This is a graph I got of sunspot number versus solar flux. And as you can see, it's not just a straight line graph. There is variation across it a lot. So if we say a sunspot number of 139 is roughly equal to a SFI, solar flux index, of about 150. But it does change a little bit. So there isn't a strict correlation between the two. As you can see, the scatter diagram shows that there isn't. But with the GB2RS, we tend to talk about solar flux indices, not sunspot numbers. I just decided that that was probably the best one to go for, and stuck with it. Now, what does that actually mean in terms of communication? Well, this is a graph of, or a prediction, if you like, from VOACAP of the MUF, maximum usable frequency, between Britain and New York in October for sunspot numbers of 10 and 115. And as you can see, if we had a sunspot number of 10, looking at that graph, you can see that would open up to America about, I don't know, is that 18 megahertz from here? I can't quite see. Mustn't get too close to that speaker. So the maximum usable frequency there was about 18 megahertz. In terms of MUF, it's probably about 20 megs, but we've only got 18 megs or 21. So you can see that nothing particularly brilliant. The other one is for a sunspot number of 115. And you can see it goes way up. So you've got almost 100% reliability at 28 megs. And you can see that the band opens up about midday on 28 megs and probably goes to about 4 o'clock in the afternoon. So this is an indication of the more sunspot numbers we have, or the higher the solar flux, the better the propagation is. And this tool we use there is VOACAP Online, which is a free tool. I'll be talking more about that tomorrow. But the thing is, years ago, we always used to use PC programs. There was VOACAP. What else we have? W60L prop. There's a whole range of them. But now we've got everything online. So we've got VOACAP Online and Propy, which is the ITU RHF prop program. So you can do all of this online and print off what you want, and you can do your own paths. So we tend to recommend using those two pieces of software online rather than running it on your own. And of course, you can do it on a tablet, you can do it on a Macintosh, PC, whatever you want, you can do it. So it's made life a lot easier. But there we go. So state of the sun, where do I get the information from? I think the easiest one is from VE3EN site solarham.com or solarham.net. I think both URLs work. It's got everything you really need there. You've got imagery of the sun, sunspot number, solar flux. Then you've got all the other data that we're going to talk about, which is the K indices. And you've also got, what else? You've got solar wind speed and direction and everything. So it's all in one place. So it's a very useful tool to use. So how many people here use solarham.com? Yeah, okay. So if you're not using solarham.com, I suggest you go and log in and have a look at it. Very useful tool, and he does a daily sort of news update with indications of what is happening and what's coming around the corner. It's also got the stereo ahead spacecraft data, which shows, so it's looking around the edge of the sun so we can see what's coming around. I'll tell you this now, we're not terribly good. I say we, I mean NOAA, I mean the Space Weather Prediction Center in America, not terribly good at predicting the solar flux index and sunspot numbers. Every week I have to do GB2RS, and I tend to write it on a Wednesday, and then check it again on Thursday, then we file it on Thursday evening to go out on Friday. And I don't think they've got it right 9 weeks out of 10. And it's embarrassing for me, let alone anyone else, but it's a problem. It's very hard to know what the sun is going to do. I've spoken to the Met Office Space Weather Center about whether they could supply better figures. No, they can't. And they will only predict up to 4 days ahead. So that's no good for GB2RS, where we need to be looking about 10 days ahead. So we're stuck. So it's a lot of guessing, really, about what's going to happen. And little hints and tips at looking at things as well, as we'll talk as we go further through, to try and work out what's going to happen in the next week. We know roughly what's going to happen in the next week, but all those little finicky bits, if you like coronal mass ejections, coronal holes, solar flares, we really can't predict them terribly well. So that's the solar output of the sun, or the photon output from the sun, if you like. We need to talk about geomagnetic disturbances now. These are the problem areas that cause the maximum usable frequency to go down and conditions not to be terribly good. And I would say the sun is constantly losing matter out into space, plasma, and it's called the solar wind. And when I say it's constantly losing matter, I mean we're talking about thousands of tons of the stuff every second. Sometimes the solar wind can be more ferocious. I used to do a podcast that I think its baseline was details of windy outer space. My word, it is windy. I mean, the solar wind is 450, 500 kilometers per second. That's not per hour, that's per second. So I wouldn't want to be caught in that wind, actually. And the solar wind can increase in its density and its speed, and it can be impacted by coronal holes and coronal mass ejections, and we'll talk about those in a minute as well. The other thing is that the solar wind has a frozen-in magnetic field. It's a plasma, so it has this so-called frozen-in magnetic field as it's moving, and that's called the interplanetary magnetic field. And we're interested in what we call the BZ. That's the magnetic B field pointing in the Z direction, as in X, Y, Z. And we always look at the BZ because if it's pointing south, it more easily couples with the Earth. So it's quite possible that you have a solar wind that's increased in speed, maybe 600 kilometers a second, but its magnetic field is pointing north, and it almost bounces off the Earth, if you like. It doesn't come in, it doesn't get coupled into the Earth quite so badly. So the solar wind is a dynamic active wind, and it can change. The BZ can change in minutes. It's constantly changing, so we need to look at that as well. And of course, if the BZ is pointing south and this plasma flows to Earth, it disrupts the ionosphere. Now, how does it disrupt the ionosphere? That is complex. So I've got an 8-page document if anyone wants it, how it actually disrupts the atmosphere. But generally, it's bad news. So solar flux index, high solar flux index is better. But if we get a high K index, which is an indication of how the Earth's magnetic field is being disrupted, it can make the MUFs drop and cause problems. Not so good. And can also trigger Aurora. So if you're an Aurora fan, yes, the other opposite. So if you're a VHF Aurora fan, you're looking for these high K figures. You're looking for Aurora. You're looking for a lot of this geomagnetic disturbance. But if you're an HF operator, on the whole, we're not. So what are coronal holes as well? These are areas on the sun that have got lower energy areas with open magnetic field lines. And so you can see there, using this Solar Dynamics Observatory, we've got a sun image on the left in visible light. And then if we look in extreme ultraviolet, you can see that we have these dark patches, and they're called coronal holes. Not really a hole in the sun, but they are areas where with weaker magnetic fields, where the solar wind can pour out. So if you have a coronal hole near the sun's equator, and it lines up with the Earth, then we're in direct line with this thing, and it's going to hit us. So that's a problem. So we need to not only look at solar flares, CMEs, we need to look at coronal holes. These were really only discovered, what was the first, was it Skylab, wasn't it? The US, Skylab. These were only discovered when Skylab was launched. So they're quite well, I said 1970s, I think, wasn't it? They're quite a new discovery, if you like. But coronal holes have been massively important over the last few years, and we now incorporate them into GB2RS because they can disrupt the ionosphere terribly when we didn't really think about them before. So to give you an idea, here's a coronal hole. The sun is rotating from left to right, and that big one that's marked 34 was the cause of the big geomagnetic disturbance there, the K index up to 5 a couple of days before. So coronal holes is another thing we have to bear in mind. So what's this K index anyway? Well, we'll come to that in a minute, but how long does it take this solar wind or a CME to hit the Earth? Well, if you do the maths, it comes out to about 2.1 to 4.3 days. So if there's a coronal hole and it's dead in line on the solar equator, and it's facing the Earth, maybe 2 days after that, we're going to get a disruption. We're going to get a disturbance. So you can almost predict if we're going to have bad conditions from that. Actually, I say bad conditions. I just should qualify that a little bit. You get when this material first hits, you do get or can get a little positive phase. So propagation can get better, and you think, oh, this is good. But it doesn't last very long, and then we get the dip. So when the K index goes up, or just before the K index goes up, it's a good time to be on HF and try and work some stuff. But trying to understand or know when it's going to hit is really hard. So if you're really, really keen, keep an eye on solarham.com. Keep an eye on the solar wind, the speed and its direction. And if you see it tweaking up on there, that's at the SDO spacecraft. Have a look on HF and you may get a surprise because things may improve slightly before we get the downturn. Now, solar flares. Let's have a look at a solar flare and CMEs. This is a coronal mass ejection coming off the sun. And I don't know if you can see down the bottom there, the little dot. That's the Earth to scale. So you can see these CMEs are massive. We are talking about thousands of tons, billions of tons of plasma flowing out. And it's the sort of thing that makes the daily newspapers, every now and again they have a, solar flare is going to destroy the Earth type story. I don't write them. But they seem to come up with monotonous regularity. So now you know what a solar flare is and a CME, so it's not going to happen. Just talk about this. So this was a coronal mass ejection of plasma coming out. They are often linked to solar flares, and you generally, not every solar flare results in a CME, but that is usually the case. So if you have a solar flare and you see a solar flare, and a CME is related to it, then that's what happens. So we'll just have a look at one of those. Now keep your eye on this white spot down the right-hand side and watch what happens in a second. There we go. Big explosion on the sun. I'll just play that again for those who didn't see it. We're looking here, by the way. I don't know. Let's have a look. I think it should be on there. Let's play it again. That's 1956 to start. And 1410, there we go. 1620. 7, 8, 9, 10, 11, 12, 13. So yeah, that's a kind of 1 hour in a minute, but that's a massive explosion of material. Good. So let's go back and talk about those again. So the first thing is the solar flare. And the main component is a massive, massive surge of X-rays and extreme ultraviolet off the solar flare. And to give you some idea, I did some sums. So the energy release can exceed 10 to the 20 joules of energy. So what is 10 to the 20 joules? Well, an atom bomb, the atom bomb dropped on Hiroshima was 10 to the 13 joules. And the world's biggest hydrogen bomb was 10 to the 17 joules. So an average solar flare is 1,000 times stronger than the biggest hydrogen bomb ever exploded on Earth. So that gives you some idea. You really don't want to be in the way of it, I don't think. So the solar flare fires up and gives us this massive surge of energies and extreme ultraviolet light, which hits the Earth in 8.5 minutes. And what's the effect? Well, it increases the D-layer absorption in all daytime regions. If you're on the nighttime side of the Earth, it doesn't affect you. But otherwise, if you listen on HF, it's a little bit like somebody switched the band off. 1 minute you're working somebody, next minute they've gone. You think, what's wrong? So you're checking your coax and checking your PLT 259s, see what dropped off, and it isn't. It's what we call a sudden ionospheric disturbance. So it's 8.3 minutes after a solar flare. It's due to ultraviolet and X-ray photons, and it's the D-layer absorption that kills it. Other type of events, we have polar cap absorptions, which is when we have high-energy protons and alpha particles coming off a CME that get funneled towards the poles because of the Earth's magnetic field. They can take 15 minutes to several hours to arrive on Earth. They're relativistic, so that's very fast still. It is still very quick. But again, that's D-layer absorption over the polar region. So this is the sort of thing that kills those over the pole contacts. So if you're trying to work Western Canada, where else would you work? China, maybe. Anything that goes over the pole, you'll hear that polar flutter. You know, the signals will break up, and CW signals can get almost unreadable with the polar flutter you get. And then, obviously, as we said, ionospheric storms, 20, 40 hours after the event, is this matter coming in from the sun, and this plasma. And again, increase in D-layer absorption and depression of MUFs. And we get Aurora. And it says sporadic E events. I think, I'm not sure about that. We have to talk to Jim. But there we go. When I say talk to Jim, I mean Jim Bacon, by the way, who's the sporadic E expert. I don't think he's really that convinced that ionospheric storms cause sporadic E. But there we go. And they vary in intensity. So you can have an X-class, where is it? Geomagnetic, X-class, X-ray, there we go, got it. X-ray solar flare. And an X1 is about the strongest we've had recently. That's described as a strong one. And that might result in a KP of 7. And we'll talk about the KP index shortly. If you start getting X20 events, you've got problems, I think, really. That's a sort of satellite killer Carrington event sort of condition we can get. And you obviously get a blackout on the Earth side of the sun. Sorry, the sunlit side of the sun. This is a graph of the GOES satellite data, and you can see the solar flares there. We've got an X2 class flare on the left, and an X6 class flare on the right, and an M class flare. M class flares don't actually cause that much of a problem, but this is just we could do without them, to be honest. The trouble is with HF propagation, when we get sunspots, we get more activity, we get flares, we get CMEs, we get coronal holes as well. So just because the sunspots numbers are high doesn't necessarily mean we're going to get good propagation. And this is a graph of the sort of effect you can expect from a solar flare. So it's an X-class solar flare, and it's these photons coming in, X-ray and extreme ultraviolet photons hitting the D layer and causing absorption. And you can see from the graph on the right that absorption is worse at the lower frequencies. So it's the sort of thing that can wipe out 5 megs and 7 megs completely, but you might not notice much effect at maybe 28 megs. So the lower frequencies are affected more and recover slower than the higher frequencies. But yeah, so if ever it seems like somebody just switched the radio off for you and the band's just gone noisy and dead and there's no signals there at all, chances are it was a solar flare. As I said, they only affect the daylight side of the Earth, but they are if you're visible on the sun's surface, they will impact the Earth. So even though you might get a solar flare happen right in one of the extreme edges of the sun, if it's visible on Earth, if you see it, then the X-rays are going to hit the Earth, and that's going to cause a problem. Whereas CMEs, if they are on from a sunspot which is on the edge of the sun, chances are that when it fires off, it misses the Earth completely. So that's the preferred option. The worst possible one you can have is a CME that is from a sunspot on the Earth's sun's equator, just exactly spotting as coming in line. So if we get an X6 class solar flare from the equator, that's going to cause real problems. And as I said, lower bands are most affected. 28 megs might not be affected at all. And you can see from that graph there the sort of attenuation effect you get at each frequency there. And at 5 megs, it's massive. Now, K indices. This is a measure, and we'll talk a little bit more about K indices in a minute, but this is a measure of how disturbed the Earth's magnetic field is. Obviously, if we've got all this plasma coming in at 650 kilometers a second, it's going to cause problems. And it gets channeled towards the poles. Actually, a bit more complicated than that. It gets channeled around the Earth to a point beyond the Earth and then snaps back and comes in. And a magnetometer is used to measure how disturbed the Earth's magnetic field is. And this is a graph from 2003. I think you'd call that a bad day. I don't think I've seen one that bad this time around. But yeah, it's an issue. Generally, we want low K indexes, low K indices for better HF conditions. But unfortunately, we're not going to get it. I think I gave a talk, was it last year, on the good, the bad, and the ugly of solar cycle 25. And I said, this is the sort of thing we're going to get. And we are getting them, unfortunately. But again, you can get graphs like this on solarham.com. And you can amaze all your friends because you can tell them why the band's poor. You hear people say, oh, HF's lousy today, I don't know why. Well, now you do know why. It's probably this. So the K index is a logarithmic measure. And we measure it around the world in different places. And then we average it out to come up with what we call KP, K planetary index. Which is the one we talk about in GB2RS. And as you can see there on the scale, I don't think we've seen anything worse than about 6 on this cycle so far, but that's pretty stormy. That's not good at all. K index of 0 doesn't happen very often, but 1 or 2 we can live with. 3, well, okay. And I think recently that it was 4 for days on end. And it's sometimes difficult to kind of work out why. We think it's, it might be the effects of a CME that's just giving us a glancing blow. Could be a coronal hole, could be both of them. They're not mutually exclusive. You can have matter coming out of a coronal hole or plasma coming from a coronal hole, and you can have plasma coming from a CME as well. And they can actually overtake each other and merge and kind of like waves coming into the Earth. So that's what it is. And the A index, actually, let's just go back one. Why do I talk about the K index and not the A index? Well, although the K index is logarithmic and only goes to 9, it is updated every 3 hours. So it's a much more reliable way of knowing exactly what's happening now, or within 3 hours anyway, where the A index is, which we're going to look at now, is only updated every 24 hours. And again, the A index is measured around the world and averaged out to give an AP index, a planetary A index. And you can see that it goes from 0 to 400 or 400 or more actually. But I generally don't use it because it's updated every 24 hours. So you could have a situation where you've got a very low A index and a very high K index, because the K index is from the last 3 hours, but the A index hasn't actually taken that into effect yet. So I don't really see much point in making a note of what the A index is. I think the KP index is far more useful and far more up to date. So we generally talk about, on GB2RS anyway, the KP index. And once it's below maybe 4, not too bad. Below 3, even better. Once it's above 6, well, you got problems. Get a new hobby for the day or two anyway. So geomagnetic disturbances are caused by this plasma coming in, and generally a high KP index, as says, means a lowering of the maximum usable frequencies and bad conditions, other than this pre-auroral enhancement, where you get an increased MUF, but it's a very short period, not for very long, maybe half an hour or an hour. And they're very hard to predict, Knowing to get on the radio just before or just after the plasma has hit the Earth, you've got to keep a really close eye on the solar wind data to get to find out when that's going to be. It was something I was going to do some research on, but never really got round to. And usually, because of the kind of geometry of the Earth and the Sun, is you normally find you get these high KP indices in the early hours of the morning or around midnight. Generally, not always, but generally they happen at that time of night because of the way it works. So the plasma is in the magneto-tail of the Earth, and it snaps back, so it comes in over the poles, if you like, usually around local midnight. And I'm not generally on that time of night, and the bands aren't generally open either, so that's why it's difficult. And so the solar wind speed can vary dramatically, typically in the range 4 to 600 kilometers per second, and it said solarham.com was the place to look for that. CME predictions. NOAA and NASA, I think, have come up with prediction methods of trying to work out when a CME is going to hit the Earth, or if it will hit the Earth. And as you can look, you see these spirals. It's a bit like a garden sprinkler, if you think. So you've got a garden sprinkler throwing this water out, and it's rotating at the same time. So you get these Parker spirals, after the guy invented them, I think. And let's have a look at what that looks like in real time. So this is a CME going to come off the sun, and then we'll see what the prediction was. These aren't terribly accurate either, I don't think, really. But that was probably the worst position it could be. So it's on the sun's equator, so it's facing the Earth, and it erupted, just as it was facing. So there we go. That's the prediction. You can see this big wave of plasma coming out. So they predict roughly when it's going to hit the Earth or hit the nearest spacecraft, which I think was the SDO one, Space Dynamics Observatory. So we have a prediction of A and K indices from both NOAA and the Space Weather Prediction Center, NOAA, and the US Air Force. Now, I don't know why, but the US Air Force is usually more accurate than NOAA's. So I generally look at the two of them and kind of think, well, what do I think? As I said, the Met Office can't supply more than 4 days in advance. So this is a lot of guesstimate work. That's the trouble. So when we do GB2RS, usually has a catch-all statement like, and if there is a coronal hole, or so if there is a coronal mass ejection, we may expect the K index to go up, but whether there will be a CME or not, we don't know, and it's very hard to predict. But you start making excuses for why GB2RS isn't always accurate, but we do our best. This is the solar wind diagram from spaceweather.com. At the top, you've got the BZ, so probably not too clear there, but that is a positive BZ, so I don't think the solar wind is going to impact the Earth too much if it's positive. If it goes down, oh, there we go, you can see it, it's in red, you probably can't see it on there. But if it swings south, so we get a southward or negative BZ, that's more likely to couple to the Earth's magnetic field, and we get problems. And the density can go up as well, that's the next row down, and the speed. So the speed there, I think it's going lower. So this is not a particularly unsettled day. This was yesterday, actually. So looking at that, you can see that the speed goes up right at the end, and BZ's kind of neutral. So looking at that, I would imagine that yesterday the KP index wasn't too bad, wasn't too high. We could have a look at that in a minute. Actually, we'll look at that now, should we? And see what happened. There we go. So this was yesterday. We can see that's probably there, that effect we saw, and then it's dulled down again and gone up again to 3. So you can almost predict what the radio conditions are going to be like just looking at this data. Once you get used to it, if you know the solar flux index, I mean, it's 160, that's good. It's October, that's good. Have we had any solar flares? Nothing major, look, just C-class solar flares on there. So nothing there really. Coronal holes? No, there's no coronal holes. So yeah, that looks pretty good to me. We could prefer it, I think, if the geomagnetic field's a little bit more settled, but I've seen a lot worse recently. So from that, I would say that probably going to have a good afternoon on 10 meters, today. So there we go. So that's how you can get to basically interpret the data using all the information we've got there. So we've got solar flux index and sunspot number. We've got A and K index. We've got the, where is it? There we are, real-time solar wind, so we can look at that. What else do we want? So are there any coronal holes? No. There we go, nothing there. This is the stereo ahead imagery. There used to be 2 satellites, stereo ahead and stereo behind. Stereo behind conked out, gave up the ghost. So we've only got the ahead one, but this gives us a little bit of a warning what's coming around the sun, because the sun is rotating left to right. So we click on that. There we go. So we've got a sunspot number is 146, but it doesn't look like it. If you started counting them, you would never find 146 sunspots, but this is why. So it's 10 points for a group, 1 point for a sunspot. So it's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. So 7 sunspot groups here. So that's 70 before you start. Then you start adding the rest up. So I just find it easier to work with solar flux indices. So 160 is far better. And programs, computer programs or propagation prediction programs, some of them use sunspot number, some of them use solar flux index. So find out which one and try not to get the two muddled up, because they generally don't tally. It's odd. At the moment, we've got solar flux index 160 and a sunspot number 146. So they're not too far apart, but generally they don't tally too well. But there we go. Right, so what's the IMF of BZ? So this is why I just talk about this a little bit better, a little bit more. So here's the solar wind coming in from the sun, and you'll see that it's impacts in the magnetosphere or magnetopause, and it gets thrown back to this plasma sheet, and it kind of gathers there at the neutral point. At which point you get some magnetic recombination, and it gets fired back to the Earth's poles, and you can see where it gets channeled into the north and south pole, which is how we get the aurora. So quite interesting. So the sun's magnetic field isn't confined to the immediate vicinity of our star. The solar wind, it carries that throughout the solar system. And they have aurora on Mars, and they have aurora on Jupiter. The only difference between the Earth's aurora and Martian aurora is that the Martian aurora can appear anywhere because it doesn't have magnetic poles. So you can have auroras on Mars at the equator, if you like. I think Jupiter does have a magnetic field. Somebody's nodding over, that's good. So it does tend to appear at the poles. But Martian aurora, no, it can appear anywhere. So if the IMF points south, we call that a southward BZ or a negative BZ. So this is the magic term to look for. That means that the intermagnetic interplanetary magnetic field can partially cancel Earth's magnetic field, and this material can flow into the Earth's atmosphere and cause us problems. So a southward BZ or south pointing BZ or a negative BZ is not good, and well, unless you're an Aurora fan. By the way, I did a trip to Iceland a couple of years ago to see the Aurora with my daughter. And we did see the Aurora, luckily, and that was with a KP index of 2. So if anyone wants to go to Iceland and see the Aurora, have a chat to me. So a friend of mine said he was going to go to see it in June because it would be warmer. I said, yes, but you won't see the Aurora. Now, geomagnetic storms are generally worse around sunspot maximum, or on the downward side of sunspot maximum, actually. On the declining side, once it was going over the hump and we're going back down again. And this shows you looking at how they've been distributed over the years. So we got past the peak, 2011, 2012. So we had a period where we didn't have too many geomagnetic storms. We are getting them now, and we will continue to get them once we pass the peak. So I suppose the word is make the most of HF now. It will get better than this. 10 meters will open up even more, but we are likely to get more geomagnetic storms. And once we get past that 2025 peak, we'll get a lot more. So now, as I said, is your best time over the next couple of years to really, really make use of 10 meters, maybe even 6 meters as well, if the flux gets high enough. But anything over, as I said, a solar flux index of about 100, 10 meters generally opens up if it's the right month. And October is a good month for it. So that's why we like to get on 10. Yeah, in fact, why are we all here when we can be on 10 meters? That's silly. Oh, and it's Newark next week. Who thought this one up? There's something wrong, isn't there? So finally, just want to talk about critical frequency and maximum usable frequency, and introduce another tool as well. This is a Digisonde plot from the Chiltern Digisonde. It's confusing. It's not Chiltern as in the Chiltern Hills. There's Chiltern in Oxfordshire, which is just down the road from the Rutherford Alpton Laboratory. This is a Digisonde. These things are quite difficult to read, so we found an easier way to do it, but I'll talk about that in a second. But basically, this thing fires radio waves straight up into the ionosphere and sees what comes back. And you can see that, I don't want to get too close to the speaker, there we go, feedback. Right, so let me see if I can use the pointer. So this area here is where it stops coming back. Ignore the green line for now, just the red line. And you'll see that it's about 7.5 megahertz. So if we look there, the FOF2, or the frequency of vertical incidence, is 7.3 megs. So that tells us that, yeah, 40 meters would be good around the UK. That's fine, and further afield. And if you look along the bottom here, this will give the extrapolated maximum usable frequencies over different distances. So you can see for 3,000 kilometers, we reckon that the MUF is 25.4 megahertz. Now, this was okay, but I was talking to Jim Bacon about this and said, they're all right. We're using these a lot, but we just needed a way to make them a little bit more user-friendly, which I'll come to in a sec. You'll notice another track up here, and that's basically the radio waves going up, bouncing back down, bouncing off the Earth and going back up again. So that is a false trace, which is double the height of that one. And you'll also notice that you've got a red and a green trace there. There's a split. And this is because the ionosphere splits the radio wave into what we call the ordinary and the extraordinary wave. Because it's going into a magnetic medium, we get this split. And you'll see that the extraordinary wave is a little bit higher in critical frequency than the other one. So we generally talk about the critical frequency of the ordinary wave, but half the energy has a slightly higher critical frequency as well. So that's what that is. We get the split there. Anyway, getting back to Jim Bacon. So I talked to Jim about this and said, is there not a way we can make this easier? So luckily he was working at his company WeatherQuest there, and they've got a really good programmer there. And they came up with Propquest, which I hope you all know. Who uses Propquest here? Oh, excellent, right. So if you go to Propquest, what we've done, we've plotted all the critical frequencies, and then we've plotted the extrapolated maximum usable frequencies over different distances. So you don't have to look at Digisonde data, and you can also call up the Chiltern Digisonde, the Fairford Digisonde, or the Dorb Digisonde as well. Is that Dorb in Belgium, I think? Yeah, somebody's nodding. That's good. So this is a great way of looking to see what's happening, and you can see the effects of coronal mass ejections on this because the MUF dives a little bit, and you'll see there. This was taken on in September. That it climbs. You know, the MUF starts coming up at sunrise, maybe just before sunrise. Generally climbs to a maximum around about local midday, and then tails off down there. But it's not a nice straight graph. It's not a nice straight progression, because the ionosphere is a living, moving, turbulent matter or turbulent subject. So yeah, it's never as straightforward as you'd think. So if you're operating very close to the MUF up here, maybe this is where you're getting openings to America one minute, and the next minute they close down again. But this, if you just mouse over where you want to go, it will tell you the MUFs over different distances. Now, this is basically, it's a guesstimate. It's a guesstimate based on what's happening at Chiltern, what's happening in the UK. So if you're trying to work south of the equator or over the pole or whatever, it doesn't tell you anything about the ionosphere in other parts of the world. This is just what's happening over the UK. But it's a good guess. And if you're really, really keen, you can call up, as I said, 3 different ionosondes to see what information you get. But you can also, there's a list you can go to and call up ionosondes from around the world. So you can check there as well. But you may as well get on the air, to be honest. Then also, what else can you tell from this? You can look for sporadic E. And sporadic E, we have a blue line there that has got stronger. And you'll probably find that that prevents the signals going higher. So you may get some sort of blocking effects on the higher frequencies due to sporadic E. So it's a useful tool. I think Propquest has worked really, really well. Chiltern data isn't terribly reliable. The Chiltern Digisonde, I don't think I'm giving too much away to saying it's getting a little bit old. It's still run on a 486 computer. And I heard they were buying up 486 motherboards left, right, and centre. And when they run out of 486 motherboards, it may not be on the air. It's a shame. We used to have quite a few amateurs working at the Rutherford Apson Laboratory, and I think they've all retired now. So it's tricky. So we decided to put Fairford in there as well, so you can check it. And if you find it's all blank, just click the Fairford one. That's probably working. Americans seem to have more money than us for this sort of thing. Good. So putting all together then, for the best conditions, we want a solar flux above maybe 150 for a few consecutive days, and the K-index must be below 2. So we need a high solar flux and a low K-index for the best HF conditions. Am I stopping people from going to lunch now? I am, aren't I? So any questions? Just to remind you that there are 2 YouTube presentations that we prepared some time ago, Understanding HF Propagation and Understanding VHF Propagation, which are still available on YouTube. They've been looked at by about 10,000, 15,000 people, but this was originally designed for clubs, but they're now put on YouTube for everyone to see. So if you haven't seen them, please go and have a look yourself. If not, any questions, or run off to lunch.
How's that? Just a question, just on the solar flares. Do you ever get these sort of enhancement MUF sort of shooting up to a great extent? Is there a 10 flare or something like that? I've heard.
X10. Generally, we don't get X10 flares, so I think X1 I think is the worst we've had for a while.
No, I think 10 flare. They mean the solar flux index shooting up.
Yeah, you may do, but generally it's going to hit the D layer. That's the one that's causing problems. So if the D layer is severely enhanced, it's never going to get to the F layer. So you may get an enhancement of the F layer, but the signals are going to be
attenuated anyway.
Yeah, attenuated before they even get there.
Just a quick observation, just a quick about the using ionograms during the impacts.
Yeah.
As opposed to just using Propquest. I think, but if you can see that the ionogram is sort of looks all beat up and all twisted and that is an indication of worse conditions on that circuit.
Yeah.
So it's not just MUF dropping, but you only get the MUF dropping effect through the Propquest. So it's my point is worth looking at those ionograms as well.
Yeah, I think people get put off by them. They're a little bit difficult to read. But I've got an animation I did over 24 hours of the of Digisondes data, and you can see the MUF rising and going down, and you can see the effects of KP index going up as well. But you're absolutely right, yeah.
I think we better close there because there are people waiting to come in. Steve, you're around all weekend.
I am.
I know you've got another lecture tomorrow, so you can catch Steve if you have any questions for him. In the meantime, thank you very much indeed.
And thank you for listening anyway.